Hello everyone, welcome to the lecture 4 of Uncertainty Modeling in AI. And today we are going to talk about variable elimination and belief propagation. A lot of the content of today's lecture are taken from the unpublished textbook written by Michael Jordan, specifically Chapter 3 and Section 4.1, which can be accessed via the two links over here. I also took some references from the other textbooks that are listed in these acknowledgements over here. I strongly encourage every one of you to take a look at these materials after today's lecture. So hopefully by the end of today's lecture, you'll be able to use the variable elimination algorithm to compute the conditional probability of a single random variable denoted as XS. That is, you should be able to compute this conditional probability of XF conditioned upon XE, where we call XF here the query random variable and XE here the evidence random variable. We'll see more detail of the definition in the following slides. And you should also be able to explain the computational complexity of the variable elimination algorithm using what we call the constituted graph. Finally, I will show the sum of product algorithm, which can be used to compute all single node marginals for tree-like graphical models. Now suppose that we let E and F be disjoint sets of nodes of a graphical model. This means that in our graphical model, we have many of these nodes, and let one of the set of this be denoted as XE, and there might be another set of nodes in the graphical model. They are linked together, but this set is a disjoint set. This means that they do not contain overlapping random variable, and we'll denote the other set here as XF over here. And XC, XF would be disjoint subset of the random variables in the whole domain. This means that there could be other random variables that are contained in this particular graphical model. So we'll choose two disjoint subsets of, and we'll call them XE and XF respectively. So our goal here is to calculate the conditional probability of XF conditioned upon XE for any arbitrary subset of E and F. And we'll see that this general probabilistic inference problem can be applied to both directed and undirected graphical models that we have seen in the previous two lectures. So now we can evaluate the conditional probability using the product rule, where the probability of XF conditioned upon XE can be written as the joint probability of E and F divided by the marginal probability of XE, where the respective marginal probability of XE, XF can be obtained from marginalizing of all the unwanted random variables, which we collectively call as XR over here, which is also otherwise known as the nuisance variables. So notice that earlier I have mentioned that XE and XF, they are subsets of disjoint subsets of random variables that can be contained in a graph. So suppose that this subset of random variables here, I'm going to call it XE, and then there's another subset of random variable which is disjoint from XE. Suppose this is the set here, and I'm going to call it XF, and these are joined together. This can be joined together via some edges, and there will also be some other random variables that are not within these two subsets of nodes, random variables. We'll call this all the other set of random variables collectively as XR, and these are our nuisance random variables in the conditional probability, or rather in the marginals from the joint probability. So we have learned from the earlier lecture that the joint probability of XE and XF can be obtained by marginalizing away XR, which is the nuisance variable, from the joint probability distribution of XE, XF, and XR, which essentially it's the whole graphical model, the joint probability of the whole graphical model that we've seen here. Similarly, the marginal probability of XE can be obtained by marginalizing away xf as well as xr from the joint probability of xf, xe, and xr. And we have seen in the first step here that the marginalization over xr is essentially equals to xe and xr. Hence, to get xe, we will simply do a marginalization over xf on the joint probability of xe and xf. Now in this figure here, it shows an example of the graphical model where we can let x6 to be our evidence node or xe, and we can let x1 here to be our query node, which we denote as x. Hence all the rest of this node over here, which is x2, x3, x4 and x5, they belongs to the Nielsen random variable, which we collectively call xr. So we will use dark shading to represent the observed random variable, and in this case here we use unshaded node to represent the query node, and we will use the lightly shaded nodes to represent all the other Nielsen variables that is in the graph. Notice that this light shading of the nodes is not a convention commonly used in graphical model. We're just using this notation over here to denote the Nielsen random variable. But in comparison, the unshaded nodes always means a latent random variable, and a shaded nodes always means an observed random variable in the literature of graphical model. Now we'll see that the marginalization of XR often involves the marginalization over multiple random variables. It expands, in other words, it expands into a sequence of summation, one for each random variable index in the set of XR over here, as we have seen in the earlier example here, where XR equals to x2, x3, x4 and x5. What this means is that we will have this summation sign over XR expanding into x2, x3, x4 as well as x5 over the joint probability of x1 all the way to x6 over here. And a naive summation of the joint probability distribution over n variables that takes k states each will incur a computational complexity of O k to the power of n steps, and this is intractable when k and n are both very large. We can see that similarly for this guy over here, to compute the marginal probability over xe in our previous example, this would involve the marginalization over x1 all the way to x5 over the joint probability distribution of x1 to x6 over here. And a naive summation of this means that we would have to go through all the entries in the joint probability here for every summation sign that we operate on. So we'll now look at the variable elimination algorithm, which is a method to allow us to compute the marginalization in a more tractable way. So we'll first look at how to compute the conditional probability of a single node xf and an arbitrary set of nodes which we call xe over here. And we'll now refer xf as our query node and xe as the evidence nodes. We'll look at how to use the variable elimination algorithm to compute the conditional probability of xf conditioned upon xe efficiently. In particular, we'll look at how to do the summation over xr of the joint probability of xf, xe and xr efficiently. Now we have seen earlier that the naive sum can be intractable. An example is given here. Let's consider the case where we are going to compute the joint probability of x1, x2, x3, x4 and x5, where the operation involves a marginalization over the Nielsen variable of x6 over here. And we have learned in the earlier lecture that a naive way of representing the joint probability distribution table of x1 to x6 will incur a size of k to the power of 6, where k is the number of states that each random variable can take. So altogether, if we were to do a marginalization, this means that we would have to go through k to the power of 6 operations to do a single sum. This means that we will incur a computation complexity of k to the power of n. This is because the sum over here, as we have seen in the previous lectures, that this sum can be evaluated into x1 all the way to x6 equals to 0 plus px1 all the way to x6 equals to 1 and plus all the way until x1 x6 equals to k. So and this is going to result in a table where we would have x1, x2, x3 all the way to x5, x4 and x5 over here, where there's altogether going to be k to the power of 5 entries in this particular table after the marginalization of x6 over here. And since each one of this entry over here, k to the power 5 entry over here, involves a sum over all the possible states of x6, this simply means that we have to go through k to the power 6 operation, which essentially means that we have to go through every single entry in this joint probability table of x1 to x6. And this can be computationally very expensive when k and n over here are going to be large. So in order to reduce the computational complexity, let's represent the joint probability in its factor form, which is given by the Bayesian network or Markov random field. So in this example here, we'll first look at the directed graph, and then we'll look at how to do this in the undirected graphical model. Essentially, both steps are the same. We'll see in the subsequent slides. But now let's focus on the directed graph, where we have this, let's consider this particular example of the directed graph over here. And the joint probability distribution of x1 to x5 is simply given by the marginalization of the joint probability distribution over x6, because x6 doesn't appear in this particular marginal probability or this joint probability distribution that we are interested in. So we will marginalize everything over x6 over here, and we can see that the first step that we do here would be a marginalization over x6 over the joint probability of x1, x2 all the way to x6 over here. And a naive way, we have seen in the previous slide that a naive way of summing up over x6 over this joint probability distribution table would incur a complexity of k to the power of n. But since we know that the joint probability distribution here encodes some form of conditional independences within the graphical model, it can be a directed or undirected graphical model. So in this case, it's a directed graphical model. We can directly write this joint probability distribution into its factorized form that is represented by the graphical model. So by now, every one of you should be able to directly write down this factorized form from the given Bayesian network that is shown in the diagram over here. And what's interesting here is that, and we can see that this marginalization operation consists of a sum as well as many product terms in the joint probability distribution or in the factorized form of the joint probability distribution. And we have also seen in the previous lecture that we can actually factor out those factors in the joint probability distribution that are independent of x6 to the left hand side of the summation. So in this case here, there's only one term in the factors that is dependent on x6. Hence, this term will still be within the right side of the marginalization of x6, whereas we can factorize out all the other terms into the left side according to what we call the distributive law of sum and products. And hence, in this particular case here, we can see that all these terms essentially remain untouched in our marginalization over x6 operation. And the only operation that we need to work on would be the marginalization on the joint probability or the conditional probability of x6 conditioned upon x2 and x5. And in this case, all we need to do would be to go through the k to the power of 3 terms in the conditional probability distribution table of x6 conditioned upon x2 and x5. And in this case, we all know that this is actually equals to 1. So in other words, we will end up with k to the power of r operations instead of k to the power of n operations, where r is so much smaller than n. And in this example, we can directly see that instead of k to the power of 6 operations, we'll be left with k to the power of 3 operations by just operating on this term itself, on this particular conditional probability distribution, which is so much smaller than the joint probability distribution of all the 6 random variables that we have seen earlier. So we'll now see that the evidence nodes are observed random variables, and hence it can be considered as a fixed constant that does not contribute to the computational complexity. Hence, the evidence nodes can be treated in a separate way where we can make use of it to reduce the computational complexity. Let us consider the example that we have seen earlier, where we are interested in finding the conditional probability of x1 conditioned upon x6. And this can be rewritten as the joint probability distribution of x1 and x6 divided by x6, where we know that we have observed x6 over here. And this is what we call the evidence node. And x1 over here is our query node as defined in the earlier slide. So since the evidence node of x6 is already observed, this means that it's already taking a certain fixed value, a certain realized value, a realization of the random variable. Hence, we can fix it as a fixed constant that does not contribute to any computational complexity. What we meant here is that it does not contribute to any form of marginalization. So there is no marginalization over x6 over here, and hence this computation can be ignored in the whole operation over here. And we'll now denote any observed evidence node as x bar I over here. So in this case, since we have observed x6, we'll denote x6 as x6 bar in our probability distribution over here. And what this essentially means is that we are taking slice of the joint or conditional probability distribution table when we observe a certain random variable to be at a certain state. Now, in this probability graphical model, in this Bayesian network over here, which by now you should be able to write down the factorized joint probability distribution of x1 and x2 conditioned upon x1, x3 conditioned upon x1, as well as x4 conditioned upon x2, and x5 conditioned upon x3, as well as x6 conditioned upon x4 and x5. So normally what will be given would be all the distribution table of the individual factors over here. Now let's look at the conditional probability distribution table of x6 conditioned upon x2 and x5 over here. Now suppose that we are given this conditional probability distribution table of x6 conditioned upon x2 and x5, where each one of the random variable takes a binary state of 0 and 1. What we meant by observing x6 means that we will fix x6 at a certain value over here. So in this case, the general form of the conditional probability distribution table is given over all the possible states, all the possible combinations of the states of the 3 random variables in this example. And what we mean by saying that x6 is taking a certain observation. So x6 taking a certain observation where it could be 0 or 1. Now suppose that if we observe x6 to be at 1, what this simply means is that we will only choose the slices of the conditional distribution table over here such that x6 takes a state of 1. This means that by writing x6 equals to 1 conditioned upon x2 and x5, where we have observed x6 to take a state of 1. Essentially what we are doing would be to choose or to pick all the slices of this conditional probability distribution where x6 takes a value of 1 and form a new table from here. So there is no summation operation over here. All we simply do would be to just do a lookup from this table and directly choose the slices where x6 equals to 1. And this would be the new probability table where we say that x6 is equals to 1 conditioned upon x4 and x5. Now putting the observed random variable or the evidence node back into the conditional probability, we'll get the conditional probability of x1 conditioned upon x6 bar, where we observe x6 at a certain state, and this is equivalent to the joint probability of x1 x6 bar divided by the marginal probability of x6 bar. So we can compute the marginal probability of x1 and x6 bar in this particular way, where we have seen earlier that we have to marginalize over all the Newton random variable over the joint probability of x1 to x6 over here. And since we have observed x6, we'll put a bar over x6, and the xr over here, the Newton random variable over here, would be equal to x2, x3, x4, and x5, since x1 is the query node and x6 is the evidence node over here. And then we'll rewrite the joint probability distribution into the factorized form as depicted by the graphical model, the Bayesian network over here, which is in this particular form. And we can see that the conditional probability of x6 conditioned upon x2 and x5 has a bar on top, where it denotes that x6 has been an observed random variable at a certain state. And what this physically means is that we are simply taking the slice of the conditional probability table at a certain state where we observe x6. For example, x6 equals to 1 in this particular case. Now we'll still follow the distributive law, where we can push in the summation into the product terms where it contains the respective random variable in the summation. Now in this example over here, we can see that x5 over here, there's two terms which consist of x5, and since x2, x3, and x4 are also contained in these two terms, this means that x5 has to be the innermost term, where we will simply write a summation over x5, the conditional probability of x5 conditional upon x3 and x6 conditional upon x2 and x5. And what this means is that since these two product terms, these two factors over here contains x3 and x2, this means that x3, the summation of x3 and x2, it better be in the outer part of the summation, which we can see over here. We'll consider the summation over x4 next, and we can see that among the factors, there's only one term that consists of the random variable x4 over here, and since this is independent of x5, which means that this term over here would appear on the left side of x5, and we can put x summation over x4 and x condition upon x2 here. And since this term consists of x2, the random variable x2, this means that x2 has to be on the left side. The summation over x2 would have to be in the outer summation of x4 over here. And next we'll consider the random variable, the summation over the random variable x3, and we can see that there are numerous terms that consist of x3 here and this term over here. There are two terms, and since we have already used this term within the summation of x5, we can write the summation over x3 condition upon x1 here. And notice that this summation here, it consists of, it incorporates all these terms within the summation over x3, which also includes this term over here. So this is technically correct. And lastly, we'll consider the summation over x2 over here. And we can see that there are also numerous terms that consist of x2. There are in fact three terms that consist of x2. This term over here, this term over here, as well as this term over here that consists of x2. And here, since x4 conditional upon x2 is already used inside here, and x6 conditional upon x2 and x5 is also already used inside the summation of x5, we can simply write the summation of x2 over the joint probability distribution of x2 conditional upon x1. And since this is in the outer summation of the summation over x3, x4, and x5, what this means is that the summation of x2 incorporates all these terms inside the summation, and hence it incorporates all the terms that consist of x2, this term, as well as this term over here. Now, finally, we'll put x1 on the leftmost side of the summation, which is outside any summation sign. This is correct because the summation does not involve x1 at all. And the next thing that we can do would be to simply evaluate the summation term one by one from the innermost summation to the outermost summation. The reason is very simple, because in the innermost summation, it only consists of all the factors within the innermost summation. It will only consist of this random variable in this innermost summation term itself. We'll start the variable elimination algorithm by considering the marginalization of the random variable in the innermost summation term. The reason is very simple. This is because all the other factors that are outside in the outer summation of this expression over here, they are all independent of the random variable x5, which is in the innermost summation. So we can start off by gradually processing the summation term from the innermost summation progressively to the outermost summation. So in this case here, we will do a summation, a marginalization over x5 on these two product terms over here, the probability of x5 conditional upon x3 multiplied by the probability of x6 conditional upon x2 and x5 over here. And here, since x6 over here, we have observed it to take a certain state, for example equals to 1, and we have seen earlier that this becomes a slice. We are taking slices of the original conditional probability table, but we will still treat it as a normal probability distribution table in this operation over here. And now let us write the result of this marginalization as m5, where 5 here represents the factor or represents the random variable that we have marginalized, and x2 and x3 over here, the random variables inside the bracket, would represent the random variables that are still remaining in the result of this marginalization. So what this essentially means is that we are marginalizing off x5 starting from two probability tables with x3 and x5, as well as x6, x2 and x5. So x6 is always equals to 1 or 0 since we have already observed it. And after the marginalization, we will be left with a table which only consists of x2 and x3, since we have already marginalized off the random variable of x5 in this case over here. So here we use m5 to denote that we have marginalized off x5 and we are remaining the random variable of x2 and x3. So in this case here, the final probability distribution table will only consist of these two random variables within the brackets of m5. And once we have done this, we can treat this as a message of m5, x2 and x3 and pass it to the next step over here and treat it as a new probability distribution table over here. And the next thing that we evaluate would be the next summation term in the outer loop over here, in the outer summation over here, and that would be the summation over x4, the marginalization over x4. And here we can see that since m5 over here, it's independent of x4, we can now push this term outside the summation sign, and here we will just need to process the marginalization of x4 over the conditional probability of x4 conditional upon x2, and we'll write this result as M4 since we have marginalized over M4 and we are remaining X2 over here. So what this means is that we are given a joint probability, conditional probability distribution table of X4 and X2, where this entries over here is P of 4, X4 conditional upon X2, and we have all the terms over here. And after the marginalization, we'll get, because we are marginalizing over X4, so the result will be a probability distribution table which only consists of the random variable X2, and we'll write this result as M4 because we're marginalizing over M4 and we're left with X2, so we do a bracket of X2, and this here, this probability distribution table over here, we'll treat it as a message which we write as M4 and X2, and we'll pass this message to the next step over here, and where this term over here will be simply just be treated as a factor or joint probability table in the factorized terms over here. And now since we see that the next marginalization that we are going to process will be the marginalization over X3, and the message of M4 X2 over here, since it consists of only X2 over here, is independent of X3, so we can push this, or we can pull this particular message over here out of the summation sign of X3, and message that we have seen earlier that of M5, X2 and X3, and since it consists of X3 over here, this means that it must be within the summation sign of X3. And there's also one other term of the conditional probability of X3 conditional upon X1, which consists of X3 over here. So we need to put these two terms inside the summation sign. And what this also essentially means is that we start off with two probability distribution table of X1 and X3. So this would be Px3 conditional upon X1. And then we have another table that we have obtained in the earlier step of X2 and X3, where this is equivalent to the message of M5. Starting from these two tables, which consist of X3 in the random variable, we're going to marginalize over X3, and this will result in a final table over here which only consists of X1 and X2. So this would be X1 and X2 after marginalizing away X3. So we'll rewrite this final probability distribution table as M3 bracket X1 and X2, and this can be treated as a message that we pass to the next step. Finally, we are left with only one marginalization term over the random variable of X2, and we can see that the remaining terms inside here consist of all the terms consist of X2 over here, where we have the first term, the conditional probability of X2 conditional upon X1, and the message of M4 on X2, which we have obtained in the previous step, as well as the message of M3, which consists of the random variable X1 and X2 over here. And notice that the message of M5, it does not appear in this step anymore, because we have already involved this in the marginalization step of over X3, as shown in these tables over here. And now we can do a marginalization over X2 on all these product terms over here. And finally, what this means is that we're marginalizing off X2, where in the end we are left with the only random variable of X1 over here, because all these three terms, they consist of only X2 and X1. Finally, since we marginalize over X2, we can write the message that we are passing over as M2 bracket X1, because we are marginalizing off X2, and we will be left with only the random variable X1. So essentially, what this means is that we have a conditional probability table of X1, X2, P of X2 conditional upon X1, and then we have a message table. It's also a probability table of M4 X2, which consists of X2, as well as another table of X1 and X2, and this would be the message of M3 X1 X2. And after marginalizing off X2 over here, we will get a table of X1 only, and we'll rewrite the this probability as m2 and x1 over here, since x2 is the term that we want to marginalize off. So at the end, what we can see here, we are only remaining the terms of x1 in this final joint probability or final marginal probability distribution of x1 and x6 over here. And x6, since we have already observed this to be taking a certain state, we don't see it appearing here anymore. Here's a more concrete example of one single step, one particular step of the marginalization, which is the marginalization of x5 that we have seen in this example. So this is the first step, the innermost marginalization that we have seen. So I'm going to show you the concrete step of how to do this computation step by step. And here, as I've mentioned earlier, that the x6 over here, it's an evidence node, and we have observed it to supposed to be equals to 1. And we're showing an example where all the random variable takes either 0 or 1, is a binary state random variable where we have observed x6 to be taking a state of 1. So here in the marginalization term, we saw that it consists of two terms: the conditional probability of x5 conditional upon x3 and the conditional probability of x6 conditional upon x2 and x5, where we observe x6 to take a certain state, and in this case we fix x6 to take a state of x1. So what this means is that the two terms, the two factors, are actually distribution tables that are given to us. So here in this case here, we have the conditional probability of x6 equals to 1 conditional upon x2 and x5 over here. And notice that in this case over here, the conditional probability here, as what we have saw earlier, is actually obtained by taking slices of the conditional probability distribution table of x6 conditional upon x2 and x5 at the state where x6 equals to 1. So we are taking all these 4 entries over here to form the new conditional probability distribution table where we observe that x6 equals to 1 over here. So here we'll get this table, and we are also given a table of x5 conditional upon x3 together with the graphical model. And now let's look at the operation of marginalization over x5 on these two, the product of these two conditional probability distribution. So here, as I mentioned in the discussion session, that this summation term can be rewritten as px of 5 equals to 0 conditional upon x3 multiplied by x6 equals to 1, because we have already observed that 6 equals to 1, and condition upon x2 and x5 equals to 0, taking a state of 0, plus the conditional probability of x5 equals to 1 condition upon x3 multiplied by the conditional probability of x6 equals to 1 condition upon x2 and x5 equals to 1 over here, since we are marginalizing over all possible states of 5 x5 over here. And here we, as I've explained in the discussion session, that we're going to end up with a probability table of x2 and x3, because these are the two random variables that will be remaining inside this marginalization term after we have got rid of the Nielsen random variable of x5 over here. And we can write down the table where since we say that each random variable is going to take a binary state of 0 or 1, this simply means that there will be altogether 4 entries in this table over here. So let's take a look at the first case where x2 equals to 0 and x3 equals to 0. We'll simply substitute the two random variable with 0 and 0 in this equation over here, in this expression over here, and we can see that this is the particular equation that we after substituting x2 equals to 0 and x3 equals to 0 into the expression over here. And what we can do now would be, since all the random variable, they are already taking a certain state, this means that we can simply look up the value from these two tables here. And I'll leave the working to you. You should check on that this example is all correct, where we are given all these entries, and then finally we'll end up with this summation, sum of product of all the entries, the respective entries from these two tables over here. And now after evaluating 0, 0, we'll do the same for 0, 1, 1, 0, as well as 1, 1, until we fill out all the table here. Now after we have marginalized over x2, 3, 4, and 5, will be remaining the marginal probability of x1 and x6, where we have observed x6 to be taking a certain state. And this we have seen earlier that can be rewritten in marginal probability of x1 multiplied by the message of 2 and x1 over here, where this simply means that the last term that we have, the last random variable that we have marginalized over would be x2, and we are simply left with the random variable of x1. Here, since we have observed x6, it gets absorbed into the message over here. And the last thing that we need to do to compute the conditional probability of x1 condition upon x6 would be to compute the marginal probability of x6 over here. So the last term that we need to marginalize, since x1 no longer appears here, would be to simply marginalize over x1 over the joint probability of x1 and x6 bar over here. And this we can immediately substitute the joint probability distribution table here, which is only consisting of x1 over here, and this would be the probability of x1 multiplied by x2 and x1 here. So this multiplication can be directly applied over all the states of 0 and 1. Suppose that x1 takes a binary state, or otherwise it can be also rewritten as it can be left as its original form, where we have two distribution tables that looks like this of x1. Then we can do the marginalization and the product in this evaluation here. But otherwise, since this is just a simple product of these two terms which consists of only x1, we can directly evaluate these terms over here. And now finally, we do a marginalization over the product of these two probability distribution table, and final desired conditional probability of x1 conditional upon x6, where we observe x6 to be taking a certain state, can be obtained from the division of these two terms over here. This term divided by this term over here. Now, following the textbook written by Michael Jordan, we will introduce a notation trick which conditioning can be viewed as a summation to make it mathematically consistent with the rest of the operation, the sum product operation that we have seen. Because earlier we saw that we have to consider this guy over here, 6 condition upon x2 and x5 separately, because we have observed x6 here. So there is no summation term over x6 in this case here, and it's not mathematically elegant. So we'll introduce the notation to turn this into a summation which can be consistent with the rest of the marginalization in the variable elimination algorithm. So to capture the fact that xi is fixed at a certain value of xi bar, in the earlier case we saw that we want to fix x6 equals to 1 and we rewrite this term here to be x6 bar, and we define an evidence potential which we call delta of xi comma xi bar, where xi bar here is the observed state of xi, and this is simply an indicator function which is equals to 1 if xi, the random variable, is taking the state of xi bar. This is the observed value. If they are the same, then the delta function, this particular indicator function, is going to return us 1 or 0 otherwise. And the introduction of this evidence potential allows us to turn the evaluations of the evidence node into summation, which is consistent with the rest of the sum of product operations in the variable elimination algorithm. And we'll rewrite this summation as g of xi bar equals to the summation equals to the marginalization over xi, and the factor of gxi multiplied by the evidence potential of xi bar. So this can be proven that it's correct, where we say that gxi bar simply represents that gxi is taking a state of xi bar, where we say that this guy here, xi, is observed to be at a constant value of xi bar. And since we define that this term over here as the summation, the marginalization over xi of gxi multiplied by the evidence potential of xi bar, we can expand the summation term over here in the usual way, where xi will evaluate this, sum this over all the possible states of xi. And so in this case here, we can rewrite it as xi equals to 0, so delta xi will also be equals to 0, and all the way until gxi equals to k, where k is the kth state of the random variable xi, and delta xi equals to k. So there will be one particular term over here where xi equals to xi bar. So in this case here, xi bar is one out of the k states that xi can take. And in this case over here, we have defined that xi equals to, when xi equals to xi bar, delta of this xi equals to xi bar is going to be equals to 1, whereas all the other terms here, they are going to be 0. And what this means is that all the other terms, when xi equals to other states other than xi bar, they are all going to drop off from the summation sign, and the only term that remains would be this particular term over here. And hence we can see that by writing it this way, g x bar I into the summation term would be simply equals to xi equals to xi bar. An example of this marginalization trick, which allows us to write the evidence node elegantly as a summation term, would be this example over here, where we saw earlier that x6 is observed to be taking a state of x6 bar conditioned upon x2 and x5. And here it will be simply, instead of writing this term in our equations, in our factorized form, we'll simply write this into the summation over x6, the marginalization over x6, and of the conditional probability of x6 conditional upon x2 and x5 multiplied by the evidence potential. So this would be a sum of product terms, as we have seen in the regular expression, and it will be consistent. It has become consistent with the rest of the expression in the variable elimination algorithm. But this term here, evaluating it out, it would simply mean this conditional probability, which is also essentially the slices, the respective slices of the conditional probability of x6 conditional upon x2 and x5, where we have observed x6 to be taking a state of x6 bar. We can also do the same for undirected graphical model, where we have suppose that we have a potential function here of psi x2, x5 and x6 bar, where we observe x6 to be taking a state of x6 bar. We can simply rewrite the message as m6, x2 and x5, where we marginalize over the random variable x6 of the original potential function over x2, x5 and x6 multiplied by the evidence potential of x6 and x6 bar over here. So if we evaluate this summation over here, we'll end up with this term where x2 with x2, x5 and x6 bar, which is equivalent to the original term that we want. So in other words, we have turned conditioning into a marginalization, which can help us to write the whole algorithm elegantly with just sum and products. So instead of just one evidence node, we can further define the total evidence node on a set of nodes, which we collectively call XE over here. And we can do the same trick where we denote this as delta XE and XE bar over here, where now XE over here represents a set of nodes instead of just one evident nodes. And this can be simply written as the product of all the evidence nodes, all the respective evidence node in the set of E, which we index by I, delta xi and xi bar, where it's equals to 1 if xe equals to xe bar. This means that all the random variables in this combination over here, where it's in the set of E, it has to be equals to xe bar. And this term over here, the product term over here, will be end out to be 1, where this makes sense because what it essentially says is that every single term of xi, where I is in the set of E, it better take the observation of xi bar and before it can becomes a 1. And when all of them are consistent with the observation in the evidence nodes, then the product of every one of these terms would be equals to 1. And the numerator and the denominator of the conditional probability of xf conditional upon xe bar can now be obtained by the purely the summation, where we can simply write the conditional probability using the product rule as the joint probability of xf and xe bar divided by xe bar, where the first term over here, the numerator term over here, can be written as a summation over xe. So in the more general form, where we also consist of the Nielsen random variable, we can rewrite this as xr xe and p of xf, xr, and xe multiplied by delta of xe and xe bar here. So this would be the more general form, which we also include the Nielsen random variable. So similarly for the denominator, where we want to evaluate the marginal probability of xe bar, if we include the Nielsen random variable, then this would become the marginalization over xf, which is what we don't want in the denominator here, since there's the only term that the only random variable that occurs here would be xe bar, and we will have to marginalize over xf and the Nielsen random variable xr, as well as the marginalization over the evidence node on the evidence potential. So we can rewrite this as xf, xr, and xe multiplied by delta xe and x bar of E, where we observe xe here to take a state of xe bar. And again, we can see that by introducing this evidence potential and the total evidence potential, we can change this equation, or we can write the whole equation more elegantly with just summation and the product operations. And it's important to note that the evidence potential is just merely a piece of notation. It's just a piece of notation to help us write the mathematics and the algorithm more elegantly. So in practice, we will not perform the summation over the function. We will not perform this summation over xe over here, since we know that this guy over here is simply slices of the conditional probability from x, f, and xe over here. We will not perform this summation over xe. It's simply slices of the probability distribution table from this guy over here. We'll simply still take the slices, and but the reason why we introduce this notation is just to make the whole mathematics and the algorithm looks more elegant. Here's a summary of the pseudocode of the variable elimination algorithm for directed graphs. So it consists of 4 major operations here: the initialize, evidence, update, as well as the normalize operation. We'll look at each one of these operations one by one. And so the first thing that we need to do would be to initialize the variable elimination algorithm, where we need to choose an ordering which we call I, such that the query node, so this is the query node F, it all appear last in this ordering of I. And here's an example where we want the evidence node, so this guy x6 over here is equals to xe, and the query node to be x1, so this is the query node which we call xf over here, and we want to choose an ordering such that this guy here appear last in the ordering. And an example here would be this graphical model or with 6 random variables, where we put x1 in the last in the order list over here, and here we can choose x6, 5, 4, 3, 2, 1, and we will do the elimination in this particular order. So what this simply means is that we'll do the elimination of x1 first, and this appears in the innermost of the summation terms, and then we'll do a x2, and we'll do a x3, and all the way until we finally reach x6 over here. So there's some terms over here, there's some factors over here, some factors over here, and there can be also multiple factors over here. So what this ordering means is simply the order of the summation that appears in this sum of product, the operation in the expression. The next thing that we will need to do would be to create an active list where we place all the potentials or conditional probabilities into the active list. And this simply consists of all the factors in the factorized form of the joint probability distribution represented by the Bayesian network. And in this example, we can see that here it consists of 6 different factors as listed here, where we will simply put one of these, every individual factor, into the active list. And what this means in the actual implementation would be, because all these factors, they're actually probability distribution tables. So the active list could be a pointer or a index that points you to all these distribution tables that is stored as a lookup table in the computer. So the next thing that we need to do would be to add the evidence potentials into the active list. And in this case over here, we saw that we have only observed x6 here, where the random variable x6 is our evidence node, and we need to now place the evidence potential, which we denote as delta of xi bar, into the active list. And here we can see that we include this x6, the observation of x6, the evidence potential of x6, into the active list. Then we'll proceed on to do the marginalization step, and here we need to marginalize according to the order that we have specified in the set of I over here. So we'll look at the first random variable in this list, which is x6 over here. What this means is that the first step that we need to do, the first marginalization that we need to do, would be over the random variable of x6. Now, the first thing that we need to do would be to search for all the potentials within the active list that contains the random variable x6, and remove those potentials that consist of the random variable x6 from the active list. Now here in this example, we saw that the 6 is contained in these two terms over here, and we are going to take these two terms out from the active list and remove it from the active list. Then the next thing to do would be to form a potential which we call phi of 6, which consists of all the random variables in these factors, and in this case is x2, x5, and x6, and we're going to take it as the multiplication of the product terms of the two factors that we have removed from the active list that consists of x6, as written in this form over here. Then finally, we will compute the message of x6, and where we are left with the random variables of x2 and x5 after the marginalization over x6. So this would be simply carried out by the sum over x6 on the potential of phi 6 that we have computed from the product of the two factors. And what this simply means is that we are going to do the operation from the two tables of x2, x5, and x6, and this would be the probability of x6 conditional upon x2 and x5. So we have these two tables from the that is referred to from the active list, and here delta x6 can be rewritten into a table where x6 equals to all the possible states of that x6 can take. And in fact, this is an evidence potential, which means that let's say we observe x6 to be equals to 1, then this guy here will be 1 and all the rest would be 0. And then we can do the sum of the marginalization of the product of these two terms, which essentially gives us the remaining probability, the final probability of x2 and x5, where we rewrite this as the message of x6, where we marginalize away x6 and x2 and x5. But what this, since this is the evidence node, what this means is that we can simply look up from the slices of this. So x6 here can take 0, 1, 2 all the way to k, and it repeats many times. So this repeats many times over all the combinations of x2 and x5. So what it means is that we will simply take all the entries here, the slice of the entries here, which corresponds to x6 equals to 1 in this example. And but a more general form of the marginalization would be the two probability distribution table, and we will simply do a marginalization, a sum over all the possible states to get the final probability distribution of m6, x2 and x5 over here. So now, once we have obtained the message of m6, x2, x5, we'll put the new message, this is the new potential, back into the active list over here. So now we can see that after a marginalization of x6, we'll see that the active list, the remaining active list, would not have x6, the random variable x6, inside the list, or because we have removed all the potentials, all the factors that consist of x6 in the operation from the active list. And the final message that we are going to put back into the active list would have already have x6 marginalized away. We'll repeat this operation. So just now we saw that we already operate on the marginalization of x6. So now we'll move on to the next random variable in the ordering list, which is x5 over here. And now the next operation would be the same. We'll look at search through the active list and find all the factors that consist of x5, and then we'll take it out from the active list, remove it from the active list. So here in this case here, we have two terms over here which consist of x5. Then we'll build the potential by taking the multiplication of these two, and then after that we will do the marginalization over x5, where as a result we will get the message m5, x2 and x3, since we marginalize away x5 and we are remaining x2 and x3, and we'll put this potential back into the active list here. And here we'll notice that the remaining potentials in the active list would not contain x6 and x5 anymore, because we have eliminated away these two random variables. After eliminating x6 and x5, we can proceed on to look at x4, x3, x2 and x1. I will not go through these steps here because it's repetitive. We'll remove the potential, form the product, and then marginalize over the desired random variable and put the message back into the active list. And here we can do it over x4, x3, x2 and x1. And finally, what we are left with would be, after we have eliminated away x1, we would have realized that the active list would be exhausted right now. So this is the terminating condition. Once the active list is exhausted, then we would have reached the end of the marginalization step of the algorithm. Here, we can see that the final product over here would be only consisting of two terms, or that is with the random variable x1, which is also our query node xf over here. And here we can do a marginalization over x1 to get the normalizing factor. So because what we are interested in would be to take x1 or condition upon x6, which we have observed x6 to be at a certain state, and this we have saw many times that this is equivalent to the joint probability of x6 x1 divided by the marginal probability of x6. So once we have reached this stage here, we need not marginalize away x1 because we want it to remain in the numerator. So this would be the unnormalized probability distribution, and this will appear in the numerator term here. But we can proceed on to marginalize away x1 to get the final normalizing factor in our conditional probability distribution. And here, this term here would be then simply written as x1 m2 x1 divided by the marginalization of x1, the probability of x1, m2, and x1 over here. So in this case, this would be the what I have talked about earlier would be the last step of normalizing the normalization to finally get the conditional probability that we want.